All right, welcome to geometry. Today's topic is inductive reasoning. Our objective today is to be able to use inductive reasoning by making conjectures and providing counterexamples for false statements. So let's start off with some definitions. Inductive reasoning is the process of drawing conclusions from a limited set of observations. When we're using inductive reasoning, we look for patterns, and we use these patterns to make a conjecture. Another type of reasoning is deductive reasoning. This is the process of forming a logical argument by using facts, definitions, and accepted properties We also use the laws of logic. We'll come back to deductive reasoning later. Today we're just going to focus on inductive reasoning. So let's look at the difference between the two. Julie notices that the floor in each of her 8 classrooms at the school has square tiling. She concludes that all of the floors in the school have square tiling. Now, since Julie notices, that's an observation. And she's only observing this in her 8 classrooms, but she's drawing a conclusion for all the classrooms. This is inductive reasoning because she used observations. She used her 8 observations of her classes, not all the classrooms. An equilateral triangle is a triangle where all sides are congruent. This right here is the definition of an equilateral triangle. Tom measures the sides of his triangle, and they are each 8 inches long. Tom concludes that he has an equilateral triangle. This is deductive reasoning. Because he used a definition. Now let's talk about conjecture. A conjecture is an unproven statement and it is based on observations. So, the statement Julie made about the floors in her classroom was a conjecture because she based it on the things she had observed. So, let's have you all make a conjecture. Analyze the pattern and make a conjecture about what should come next. Draw this pattern of polygons and your conjecture on your note sheet. Go ahead and take a minute and try this out. There are multiple correct answers. And our final topic for today is counterexamples. A counterexample is a specific case for which the conjecture is false. So, after studying the figures below and making an observation of the right angles formed, so each of these blue lines has a right angle with the black line when they intersect. One might make the conjecture that all bisectors, meaning they cut it in half, of a segment make a right angle with the segment. Now, it only takes one counterexample to prove a conjecture is false. So right now, this blue line cuts the black line in half, but I could also draw this red line that still goes through the middle of the black line and cuts it in half, but it's not perpendicular to it or forming a right angle. Also with this one, I could draw a line through there. It's still cutting the black line in half, however, it's not at a right angle. And again, with the third one. Now, those were 3 counterexamples. Technically, we only needed the first counterexample to prove the conjecture false. So let's look at some situations. We're going to show these conjectures are false by writing a counterexample. So, our first example, all triangles are equilateral. Well, if you remember from previous math classes, there's more than one type of triangle. A scalene triangle has no congruent sides. And we said earlier when Tom was making his conjecture that an equilateral triangle, all sides are congruent. Scalene triangles, all the sides are different lengths. Number 4, no quadrilateral, which means it has 4 sides, have congruent sides. Can you think of a shape that has 4 sides and all of the sides are the same length? That's right. A square is a quadrilateral. with all congruent sides. And for our final example, if the floor has square tiling, then I must be at school. Take a minute and think, is there a place that also has square tiling but isn't school? Go ahead and write down your counterexample. And the final piece of our notes, in your summary box at the bottom, compare and contrast. Describe the differences and similarities between inductive and deductive reasoning. That's all for today. See you in class.